Welcome, everyone. I should say, as you're joining the room, make sure that you are muted, as Paula will be speaking soon. Welcome to the 2020 Center for Aspen Center for Physics online colloquia series. Today we have Paula Jofre of the University of Diego Portales. I'm Keith Hawkins. I'm at the University of Texas at Austin in astronomy, and I'm a co-organizer for the Aspen workshop on galactic archaeology with fundamental stellar parameters, synthesizing the power of accurate ages with distances, chemistry, and kinematics. Our workshop is centered around bringing together experts in time domain astronomy, astrometry, stellar evolution, galactic dynamics, galaxy formation, and cosmology in order to fully utilize the significant explosion in data that's now becoming available with surveys and missions like Gaia, Kepler, TESS, and other large spectroscopic surveys. While we planned to initially share and develop these new ideas in astrophysics with these new data sets in Aspen this summer, due to the recent state of events, of course, we cannot actually do that, though we can bring at least a little bit of a flavor of this here in this virtual colloquium series. So new this year, the colloquia will be posted on YouTube at Aspen Physics. And you are invited to share the recording with the students and other colleagues. The center is also going to be hosting public lectures online, and there will be another public lecture on this Thursday. They're hosted every Thursday at 5:30 Aspen time. This Thursday, there will be a public talk from Lisa Randall of Harvard University, whom some of you may be familiar with, and she will speak on darkly charged dark matter. Since Paula's talk is only roughly 30 to 40 minutes, we won't interrupt her during her talk. But if you have any questions at any time, please use the raise hand feature by clicking the raise hand button at the bottom of your screen. And I will call on you during the Q&A period after Paula's talk. Also, just as a note to everybody, this talk is being recorded by the Aspen Center for Physics, so you may appear in that recording. If for any reason you do not want to appear, please stop your video if you don't want to be seen. Okay, so I'm pleased to introduce our speaker today. Paula Jofre is our colloquium speaker, and she is an assistant professor of astronomy in the Núcleo de Astronomía at the Universidad de Diego Portales in Chile. She studied astronomy at the Pontificia Católica University of Chile and obtained her PhD from the Ludwig Maximilian University and the Max Planck Institute for Astrophysics in Germany. She then moved on to a postdoc at the Laboratory of Astrophysics at the University of Bordeaux in France, and then onward to as a postdoc at the Institute of Astronomy in King's College in Cambridge, the University of Cambridge in the UK. That's actually where I first met Paula, and it is my great honor to give this introduction because Paula was, in fact, one of my PhD supervisors when I was a graduate student at the University of Cambridge. Paula is a world-leading expert in galactic and stellar astronomy and is particularly well known for her unique, fresh, and interdisciplinary approach to the field, melding ideas from biology to those in astronomy. And her work has recently been recognized by many, including most recently being awarded the 10 Scientists to Watch by Science News in 2018, and she was chosen as Time's 100 Next in 2019. So it is my great pleasure to welcome Paula to speak to us this morning about galactic phylogenetics. So take it away.
Thanks, Keith, for this introduction. Yeah, it is a great honor to give a talk here. I see a lot of participants and also a lot of names that I know and people that I know that we discuss a lot in meetings and that now I miss a lot because we cannot do that. So these are great opportunities to feel close and to share about the latest things that we have been working in this direction of phylogenetics. I just want to make the comment that this idea of putting together biology with astronomy came out of discussions in King's College, and I joined King's College because Keith Hawkins was a student there and he encouraged me to do so. So at the end, it's kind of all chances of life that come together and then these kind of things happen. Yes, so I'll talk about this funny thing of interdisciplinary of putting biology and astronomy together. The language, it's complicated, the concepts are complicated, and I'll try to make it as simple as possible in this talk. That means that I may be discussing things or introducing things that are very basic for some, but may not be very basic for others. I hope that we can, like this, all learn a little bit about this. So I know that the word phylogenetics is not familiar for many people outside biology. So maybe a better title for this talk should be something like this. If I can move it. Oh, why I cannot do that? Wait a second. My talk is frozen. Let's wait. Let's make play again. Yes, so another title would be rather using heritability in galactic evolution instead of this funny word of phylogenetics. But at the end, I want you to know what means phylogenetics. So we want to study galactic evolution. And for that, we want to use tools from biology and from other evolutionary studies. And these tools are all around this concept of heritability. So what does it mean, heritability? That is capable of inheriting. So if I go to Wikipedia and I try to understand what means heredity and heritability, it means passing on of traits from parents to offsprings. So through heredity, the variations between different individuals can accumulate. And these variations is what cause species to evolve. If there is no variation, there is no evolution. So why it's frozen again? Sorry about this. Now my computer is completely frozen. Sorry. I will stop the share.
Sharing does not work particularly well with the full screen mode. So you might just show that it's in the slides mode. You will lose.
No, maybe because I was using, let's.
No, it really is a common feature of Zoom. So with many computers, so that's how it is. So just show the slides and not the full.
But if I show the slides, I cannot show you my animations.
Yeah, that's a problem.
Let's. I'll took out the. Let's give it another go, and if not, share. Okay. Is it okay like that?
Yes.
Yeah, it's fine.
Yes. So, okay. So as I was saying, the traits is what we need to know that pass from one generation. No, sorry, this is not working. That is true. It really freezes. I cannot even go out of there. I will follow your advice if I can. Sorry about it. Okay. Yeah, it's going to be not with so many animations. It's a pity because I had a lot of it because I thought to make it more dynamic since this is a Zoom talk. So anyway, let's start from the beginning. The idea here is to use phylogenetic trees, which is use the principle of heredity to understand how can we do galactic evolution like this. So phylogenetic trees are a fundamental tool that is used to reconstruct and study evolution, because these are a form of visualization of the hierarchical differences that are produced as the variation in these traits are accumulate over time. So if there is no variation in how information is passed from one generation to the other, then there is no evolution. And the phylogenetic trees are a visualization of that fact. So we can use phylogenetic trees to make it, to study chemical evolution in these galaxies. So then, actually, when I was once in a meeting in King's, there was a biologist who I think that is in the audience as well, who showed for the first time phylogenetic trees to me in a way of saying, this is how we study evolution. And then we made this question, can we make a phylogenetic tree for galaxy evolution? And that led to a second question, which is, can we, what is the heredity principle in galaxy evolution? So then we need to come to the next question, which is, what are the traits in chemical evolution or in galaxy evolution? And the traits are the chemical elements. So because we know that the chemical elements are made in stars and only made in stars, and as stars shine, they produce heavy elements out of fusing light elements. So at the end of a stellar lifetime, new elements are produced. So this is how the information about evolution is passed from one generation to the other in the universe. So in this nice presentation figure here that you probably won't see because I cannot put the full screen, but here we have a beautiful molecular cloud, which are essentially the birthplaces of stars. So as this molecular cloud collapses because of gravity and condense, stars are formed, and we form stars stars are formed in different masses. So they have the same chemical composition in this cloud, but then there are different masses. So there are big stars and there are small stars. So in this figure here, eventually a big star should appear next to this small star. Here there is a big star. So big stars and small stars, the difference between them is their evolutionary time scale. So the big stars or the massive stars very quickly die. They very quickly run out of the fuel and then they die, while small stars or low mass stars, they do that in much longer time scales. And that means that there are small stars that are even today alive in the universe and that they were forming very, very at the beginning. So when big stars die, they explode, and because they were creating new elements inside them, these elements are sent back to this interstellar medium and to these molecular clouds. And then a new star formation episode happens in this cloud, which is different than the previous one. It is now more enriched in chemical elements because the previous generation had stars that died and donated this material into this interstellar medium. So two generations of stars, which are now here, the white and the red, they are connected to each other via their differences in the chemical composition. So for the state of the art in the field, and this is what we wanted to discuss in Aspen, is to put together all this wealth of data we have about these low mass stars, because since they are long lived, at the end, most of them, or most of those that we see in the galaxy, these are these low mass stars because they live for so long. So we have them of different generations. So Gaia, which is the main symbol here, has been revolutionary because Gaia now has given us billions of positions and motions of stars. And now we can complement the information that we know from Gaia, from the movements and the positions, with the information from spectroscopic surveys, for which we can derive chemical compositions like these icons here, which are different spectroscopic surveys that are placed in different parts of the world. And also we can complement the information with these other space missions like Kepler, Corot, TESS now, and Plato in the future, which are giving us information about how stars oscillate. And these oscillations are helping us to know better what is the interior of the stars, and like this we can understand better their masses and hence their ages. So the idea is to put all this information together and like this see how can we constrain the models for galaxy evolution, using this idea in mind that the chemical composition is tracing the evolution with particular emphasis. So we are in this area of millions of stars. This is why we wanted to have this workshop. And we wanted to discuss these things because we're in this area where computers somehow efficiently can analyze millions of spectra and millions of data with these new machine learning and data-driven techniques. And at the same time, computers are now able to model stars from the interior all the way to the atmosphere. And like this, we can improve the accuracy of our stellar parameters, which is needed for making these training sets, which are then used to train these machine learning algorithms. And like this, we can have this information of the stellar parameters for millions of stars. So I wrote an annual review, which was published last year, which I invite in particular all the students that are in this audience to read about it, because we discuss a lot about the challenges of reducing the uncertainties in these measurements, in particular of the stellar abundances, and also a very important subject, which is to put the different spectroscopic surveys, because each of them have different instruments and are targeting different kind of stars, to put them at the same scale, because then for constraining a model of galaxy evolution, we need to complement this data. And this is a tricky business, and a lot of that is discussed in this annual review, which I will not enter here to move to the trees. But the conclusions here about what is going on in that part of this field is that because thanks to these new methods that are being developed, abundances are getting incredibly precise. So the error bars are very, very small. But we're still having a lack of a complete training set. So the abundances are not getting so accurate. And then the scale between the different surveys is still quite large. So there are systematic uncertainties there that are still a big problem in the field. And these are main topics of discussions in the field. Unfortunately, accuracy is not a sexy topic, and therefore it is getting really hard to get support to improve the training sets, either from fundings for projects and even from serving proposals. So of the 10 proposals that I wrote until last year, all of them have been unsuccessful. And this is actually something that we as a field should also try to change a little bit and work a little bit more on unsexy but so needed topics. Then comes the more sexy bit, which is try to put together all this information, assuming that we have solved the problems of accuracy and precision. We still need to face the next challenge, which is to put sense to these multidimensional data sets. And in that way, how can we use all this data to constrain the models of galaxy evolution? And for that, we need to revise a little bit what the abundance ratios mean. What these measurements for the different abundance and chemical abundances from the spectra tell us about galaxy evolution. So here put an abundance ratio of an element Y, X and element Y. And what do they mean? So in abundance ratios diagrams is something we use a lot in astronomy. And this is because, as I said initially, elements are produced inside stars, but they are produced at different quantities and at different time scales according to the progenitor mass. So more massive stars would quickly die and donate these abundances to the interstellar medium, while lower mass stars would do it at a longer time scale. But also the quantities are related, are depending on that. So the abundance ratios help us to disentangle the different nucleosynthesis processes happening inside stars. And like this, we can also disentangle the different star formation histories of the different stellar populations we may be having. So one typical alpha abundance ratio diagram is the alpha metallicity plot. That means alpha would be elements that are produced via the alpha captor, like oxygen, magnesium, silicon, calcium. And they are produced mainly inside the massive stars, which again are short-lived. So very quickly, a lot of alpha is sent back to the interstellar medium via explosions of these massive stars. On the other hand, iron is produced mainly by supernovae of binary stars, so of low mass stars. So one of these low mass stars gets mass from its companion and it explodes, and they produce a lot of iron. But because the stars are low mass, this happens after or at a longer time scale than alpha elements, for example. So at the beginning of the universe, imagine that this was like my slide that was showing off step by step. At the beginning of the universe, we had a lot of alpha elements, and we didn't have so much of iron, because iron, these low mass stars didn't explode yet. But then at the end, they say now, we have still quite a lot of alpha elements, but lesser than the beginning in comparison with iron, for which we have much more, because we have had enough time for many of these low mass stars to explode. So a typical alpha metallicity plot would look like this, and alpha over iron would decrease as a metallicity increase. So these plots can help us to interpret how is the evolution, or how is the evolutionary history of galaxies. And this is done nowadays for in the field for many elements, because now we have we can disentangle alpha's element and other elements from the spectra. So we can have, for example, here one oxygen, and I will have to remove it like this, or we can have also many other elements. So here this is oxygen over iron, and then this is a model trying to constrain a little bit the metal production, for example, of each of these individual elements separately. If we then consider also the ages of the stars, we can make more panel plots of these alpha or these abundance ratios, but then color code them for the different abundances like titanium, yttrium, strontium as a function, color code them by age. So we know how to determine ages from these, for example, Corot and Kepler, and we can test in the temporal evolution of these elements. And then we can do the same if we take into account Gaia. So we can have the multi-panel plots of the different abundance ratios, but now distributed in the galaxy. R means the distance from the galactic center, and the V5 would be the circular velocities of the star. So we can make maps in space and in motion for these chemical abundance ratios. And this is all great. So we are, this is so annoying that I cannot put for my full screen. That was the first emoticon. So we are very happy because we have so much data, and we can put all this data together and play with all this data. But then the more elements we have, because we have so many from this high resolution spectra, and the more information about the kinematics we have from Gaia, and the ages we can have also as they improve, we can start having a lot of multi-panel plots that become actually quite complicated. So then we have so many dimensions that our 2D plots alone cannot help us very much to reconstruct the history of the Milky Way. So we start making us the question with that emoticon instead, like, oh, we should, you know, our abundance ratio should go up and down as a function of what? And then we are completely confused. So this is when tree thinking can be of great help, because this can allow us to visualize the data not in 2D plots, but in another thing which is meant for interpreting evolution. And these are the trees. So again, if the traits for heredity in evolution of the galaxy are the stellar abundances, then we can collapse all the stellar abundances into a phylogenetic tree, and like this we can reconstruct the history. So for doing that, we have on one hand, kind of our input would be the trait inheritance, which is essentially the chemical abundances of the stars. And they evolve differently with time because of the mass of the star and so on. And then our output, that is things that we could interpret from the tree, would be the environmental dependencies, like galaxy interaction, that would mean interaction of the gas coming from the different galaxies, putting together the galactic dynamics, because stars move from their birthplace and they go elsewhere. So that is also something that we can maybe see in our trees. And also processes, physical processes like feedback from the supernovae, and also how is the role of the density of the gas in forming new stars, because this is then translated in chemical enrichment rates changing. So we try to make stellar trees, and I'll show you here one of the first ones. You know, before we need to define what will be the traits. So for that, we have to choose abundance ratios that evolve with time. And we can combine abundance ratios as we saw before. We don't need alpha over iron only. We can play, because we have so many abundance ratios, we can play with different abundance ratios in order to get those that are evolutionary dependent, that change with time. So here there is an example of such traits. And we built now, and we just submitted this work of a tree of 80 solar twins in the solar neighborhood. And I hope that this will come up soon, that you can see the paper eventually in the archive. These stars were analyzed actually not by me, but by Bedell in this paper. So they determine the abundances and the ages in a very precise way using specific techniques to analyze solar twins. So the tree would then look like this one here. So I'll spoil again all the surprises, but essentially this the distance on the branch length is the chemical distance of all the traits that we have inputted in the tree, and then stars that are closer together in the tree are closer together in chemistry, while stars that are further away in the tree have a longer chemical distance. This tree looks very funny. Firstly, it doesn't have a root, because if we would like to put a root on the tree, which would kind of tell us where is the beginning of all of it, we would need a chemical evolution model, which is something that at the moment we don't have for this kind of analysis. But the colors of the stars reflect the age. So the blue stars are old, and then the yellow stars have intermediate age, and then the red stars are young. These are the ages that were determined in this work by Megan Bedell, and are put here only for reference. And we can see that there is a signal of evolution, because we can see that it goes from old to young in the tree. We can also see that the tree is in balance. So we don't have, for example, a branch here and a branch here and a branch there, but we have a main branch going on over and kind of suggesting a preferred evolutionary path. And finally, we can also see that there are some anomalies in the tree, like this one here that is circled with red. These anomalies can tell us something about an important process that was happening in the evolution of this system. Here, for reference, is the sun. It is also in a small anomaly. So if we can look this tree in a different way, and we can plot it not in this unrooted form, but in this classical form, which is seen here. If we turn it, so there was we can connect this point here with this one here, and display the tree in a rooted, in a classical form. And we can color code the stars in groups. So we just choose 4 groups according to how they are placed in the tree. And we can study a bit further how is the chemical compositions in order to see if we can associate these groups towards some stellar populations that have an astrophysical meaning. So first we see here the chemical compositions of the stars, and we see that and here I plot the mean and the standard deviation of all the stars in a given group. So we can see that the blue stars are alpha enhanced. Here, no, this is the alpha capture elements. We can see that the yellow stars, they have a very low dispersion in the abundances in comparison with the rest of the groups, and this happens in all the abundances here. We can see that the red stars are enhanced in these neutron capture slow process abundances, but are also alpha poor. So we can explain this behavior of the chemical elements using principles from chemical evolution. So that is encouraging, because it tells us that the stars are kind of related through chemical evolution principles and are not just randomly placed like that. We can also see what the stars are doing in phase space, like how they are moving and where are they placed. And these are these 2 plots that are shown here. Here we show the ages of the stars as a function of the eccentricity of the orbits. And here we show the birth radio, or the distribution of the birth radio of the stars for the different groups. We can see again that the blue stars are old and that they are kinematically hot. So there is a range of eccentricities for the blue stars. We can see that the yellow stars are still old, but not as old. And they have, what is interesting is that they come from different parts in the galaxies, not that they are coming from a given region. Considering that they were very homogeneous in their chemical compositions, one would expect that they come from one region in the galaxy, but actually they have a wide range of birth radii. And the red stars, they're kinematically cold, so they are mostly on circular orbits, they're young, and they are born locally. So this is actually the location of the sun with respect to the galactic center. So that means that we can separate the stars according to some stellar populations that have an astrophysical meaning, and we can attribute these groups to different stellar populations that we know. We can say that the blue branch here, the blue stars are the thickest stars, and these two stars here are the thinnest stars, or these two groups are the thinnest stars, and then these yellow stars here, we can attribute them to something we call a burst, like a star formation burst, as we will see after. So if we turn around this tree, again, for making it more easy for us to link it to the previous tree, we go here. Here we have the thickest, the burst, and the thinnest, and we can then connect that this branch here, which was the branch here, is the thickest. This is the burst at the stars that are in this anomaly here, which is the burst stars, and then that branch, long branch here, would be then the thinnest. And like this, we can then interpret a little bit the history or the shared history of all these stars together. So the first thing is that the thick disk is then an ancestral population of this system. So it's not an independent one, but it's maybe an ancestral one according to the interpretation of this tree. And the fact that they are kinematically hot could be related to that they were puffed up because of a major merger that may have happened about 8 or 9 gigayears ago. This is something we know from the literature, that this major may have happened, but it only heated up the stars, not the gas, and therefore this thick disk became extinct. The burst star, they are in this anomaly, which is called a polytomy. And polytomies may hint towards a significant change in the evolutionary time scales. So in this sense, it could hint towards significant change in a star formation rate. So if this could support that if this major event happened 8 to 9 gigayears ago, that merger may have deposited part of the gas in the disk and may have mixed the gas that was in the existing disk with the new gas coming in, and that could have triggered a star formation burst after the major merger event. And because of the ages of the stars are between 6 and 8 gigayears, so this is 1 or 2 gigayears younger than when this event happened, it could be explained that this is a star formation burst that was produced from such a major merger event. And after that, the gas can settle again, and then star formation resumes normally and quiet until today, which is reflected in this new branch coming here with a very clear hierarchical structure. So to finalize our tree of 80 stars, which is very little in comparison with the millions of stars that we were speaking before, but it's very encouraging to see how it remarkably tells this unified story of what we have been already finding from several different and independent works. We know from the literature, which is something very active at the moment, like every week there is a paper about this in the archive, that there was this major merger event about 8 to 9 gigayears ago. People call it Gaia Enceladus or Gaia Sausage, according to these two works that have firstly shown it with the Gaia data. There is a lot also in terms of the advances of simulations that expect that the Milky Way interact with other galaxies, and they predict also that each of these interactions may drive changes in the star formation episodes in the main galaxy. So the fact that there is a time delay for a star formation burst after a major merger event agrees very well with the ages of the stars we have here. We also, from recent literature, we have seen that there are many studies, mostly on the dynamical part, but also combined with chemistry, that shows how the disk has a lot of little events that are altering star formation. And we have the potential to study them further when we have more stars to put in our trees. So I finish then with the main conclusion that phylogenetic trees are used for many different evolutionary studies. And here we show how we can use them for studying galaxy evolution. And I finish here with, this is how this idea made it to be part of time. But yeah, there is a lot to understand. The progress is really slow because each of the steps is associated with a lot of questions. So we do a lot of thinking on this and progress very slowly. but we're persistent and we're very excited. In particular, these kind of recognitions are very encouraging, and we feel that we're opening a path into this jungle, and that's kind of very cool. So I finish here, and I'm sorry for the technical details. I hope that you could follow, and now I can answer questions you may have.
Okay, thank you, Paula. I'm going to react with a clapping sign because we can't all clap. If there are any questions, again, please use the raise hand feature. There's a little raise hand button at the bottom of your screen, and I will make sure to call on you to ask your question. So I think the first question here is from Daniel. You want to unmute yourself?
Yeah, hi. Thanks. Very interesting. I had a little trouble following. Are these, sorry, baby talking. I had trouble finding how the trees are phylogenetic. So when two stars are near each other on the tree, it doesn't necessarily mean that they share a common history, that they formed out of the same dust particles, right? It just means that they're similar. Now they could be at opposite ends of the galaxy or whatever, right?
Yes, so in principle, the postulation here is like, and it is the same postulation than the principle of chemical tagging, which is something that is also quite active in the field right now. If two stars have a very, very similar chemical composition or identical chemical composition, if you go one step further, you may assume that these two stars were formed from the same molecular cloud and that they are siblings in a way. So if two stars have a slight difference, they should be kind of evolutionary very connected. So the more different the stars are, the more evolutionary time must have happened between these two stars. Of course, then there is problems that if you don't know, I mean, it is very possible that you may have two stars that have exactly the same chemical composition, but are completely disconnected and from completely different parts of the galaxy. But in that case, then of course, here we will have a big problem, and this is the same problems that we're facing for chemical tagging. These are things that we don't know, right? And actually, in a way, I think that if it should not be like that. I mean, we need to simplify our models for galaxy evolution, and we need to assume that things are symmetrical and that they're evolving equally everywhere. But actually, because each of the supernovas are so different from each other, I don't really see that this is the case. The question is like, can we measure the differences? And probably we're far from being able to measure this very, very tiny difference. But I suppose that a star here and a star there, they cannot be identical because they must be tracing different histories.
Great. Rui, I believe, if you can unmute yourself.
Okay, thank you for the fascinating talk. I have a question that's kind of a little bit maybe unrelated, but you mentioned the machine learning for the studying, to analyzing the data now, but my question, I'm interested in machine learning. My question is, exactly what kind of machine learning are typically used for this kind of data analysis? You mentioned probably, it seems like a supervised learning, but do you also do like unsupervised or other kinds? And also how important machine learning is nowadays or in the future for this kind of a task of, I mean, observatory astronomy or astrophysics in general? Thank you.
So yeah, so machine learning is now kind of a very active topic in the sense of determining the abundances of the stars from the spectrum. At the moment, I am not aware of any tool that is doing unsupervised machine learning. So they are all based on some training set for which we can control better the information about the stellar properties. Things that are being used are some data-driven approaches, and also a lot of artificial neural networks are coming up. But this is all very new, actually. So actually, for my annual review, when I wrote it, it was like when it was really starting. So at that time, there were like 3 or 4 papers in the archive about it. And now it is kind of going on a boom. So I think that in the next, I would say, 5 years, it is going to be a completely revolution about what are the tools that work and which are those that don't work. At the moment, it is still kind of everything oriented towards supervised, in the sense that there is a set of reference stars that need to be there, for which we can control the uncertainties when we know what are the abundances of the stars. And then the problem is like how needs to be this reference set, because it needs to be kind of a representation of all the stars in the galaxy, but on the other hand, we cannot really know, this comes back to the previous question, we cannot really know that the stars that we are observing here will look exactly the same than the stars elsewhere in the galaxy. So we are kind of, I think that having also some kind of fundamental problems about how to construct these training sets.
Thank you. Can you provide a couple of reference on this? You said you wrote a review paper on this,
yes.
Right?
So
maybe send a message or something.
From there, and then you can follow. What is it? Here, that's
Okay.
the code.
Okay, got it. Thank you.
Cool.
Great. Kate, if you want to unmute yourself.
Hi, thank you. And thank you, Paula, for this beautiful presentation. I really like this framework. You showed a slide that had the birth radii for the 4 groups of stars that you spoke about.
Yeah.
And I was wondering, so in particular, I was interested because there is a bump for 4 of these populations that is about a kiloparsec, it looks like, inside the solar radius. And I was wondering if you could talk a little bit about the assumptions that went into determining the birth radius in particular, but also about your interpretation of that. Because I find this result particularly intriguing.
What, I mean, okay, so you mean this one here? Or you
yeah,
mean...
so all of them have there's a lump, right? So there's there's a lump for the, sorry, go ahead.
Yeah, so I think that, yeah, that is very interesting. I mean, here, when we have only 80 stars, and when you divide it in 4 groups, each of the groups is very small. So all these bumps kind of maybe just have, you know, may not be significant on one hand. Also, like, in order to really investigate, and this is kind of where we are trying to go ahead in the future, because in order to really kind of investigate, for example, the distributions of these birth radii, you know, for the different populations, we would need to have samples that are better, you know, where we can address a bit better the selection function. In particular here, we restricted ourselves to a study that was not meant to be for doing necessarily galactic studies like this, because it was chosen from data that was already observed in the literature for solar twins, which are stars that have a given metallicity, so this induces the first bias. And secondly, these were spectra taken for the archive because people were interested in finding which of the stars had planets. So they were just chose because of another reason. So it is a bit difficult to make a kind of robust analysis on the dynamical properties of the stars, because we don't really know what we may be missing. So in particular of all these gaps, we don't know, because these stars were not selected to make a kind of volume complete sample of populations in the solar neighborhood. The problem is that when you start having when you start having a volume complete sample, then you need to start accounting for different kind of stars. So then you start inducing biases in your systematics in how you determine the chemical abundances. So then you need to be very careful, because if then the chemical abundances difference may be a systematic because of the different techniques that you need to employ in order to retrieve the abundances. So here we wanted the differences in the chemical abundances to be true, to be real, because the stars are very similar to each other, but then we need to be aware that these gaps and all these things in chemical space, in dynamical space, may be not real, because we are having gaps in that direction.
Thank you.
Great. Paul, I believe he has his hand up. If you'd like to unmute yourself.
Yes, Paula, could you say a little bit more about the merger event that happened 8 or 9 giga years ago?
So we know there are many works on this right now in the literature, and it's and now there is evidence, although there have been studies that are actually even from before the 90s that have already made some claims and some suspicious about it. But we know that about that time, which is like 2 gigayears after the formation of the kind of proto-galaxy, the Milky Way experienced a major merger event with a galaxy that was about 10% the size of the Milky Way. And at that time, the disk was just starting to form. And when this galaxy crashed with the Milky Way, now we are kind of, we believe that made that some of the stars end up heated, so kind of puffed up. So, and that produced what we call the thick disk. So these are stars that have now an extended, that they have orbits that are a bit away from the galactic plane, but then that galaxy that also had the gas, deposit the gas in the disk, and this gas was mixed with the gas that was already existing there, and that kind of changed a little bit the chemical composition of the galaxy in a way, and triggered new star formation, for which then the second disk formed, which is the thin disk now. So we think that the stars of this accreted or this merged galaxy, because this galaxy also had stars, these stars were deposited in the Milky Way halo, not in the disk. So they are orbiting in the galactic halo, and they have actually a different chemical composition than the stars in the halo. And this is some of the things that we have been working on.
Thank you.
Question from Gloria, if you'd like to unmute yourself.
Hi, thank you for the very interesting talk. I'm curious about the uncertainties and how you would handle it. How do you handle them in your classical tree? For example, is it possible that within the uncertainties that you have, you may be seeing, for example, a binary population? Like most of these stars are maybe assumed to be individual, but maybe some of them are binary. So would they show up somehow, and could you identify them?
Yes, so, okay. There are many uncertainties. So we did a lot of standard tests to account for that. We did lots of bootstrap analysis in order to remove some of the abundances to see what was the stability of the tree. And then, for example, and this is kind of, this tree is the most likely tree to happen among all these realizations. So each tree, when you change a little bit the measurements, will lead you to a slightly different tree. So this is the tree that appears most of the times, and this is the tree that at the end was selected to be the most probable one. But then we, for example, we collapsed the branches that were so small, that were smaller than the uncertainties in the measurements, because then you cannot really know whether this star goes before or after if the differences are so small. So all of these are collapsed, and this is what produced this kind of polytomies here. You can see here that you have a lot of branches coming out of the same point. And this is because we cannot really tell whether this goes before this one or this one of the other one. So they were actually artificially collapsed to produce these polytomies. And this is, at the end, it is reflected in the burst, right? So the stars are chemically so similar that we cannot really find a hierarchical structure there, because they are very similar. And this is why we have a kind of big polytomy here at the end. Then there is this particular star here, which is very long, and it is located here. I mean, we can see it maybe in this plot here. That one here is very long, and it has a different color. Actually, it is a bit redder star, which means that this star is a bit younger than its stars that are more similar in their chemistry. We believe that that star there is a binary, actually. Although we looked for signatures for binarity, and there is nothing about it. But then the sample had other binaries that we had to remove, because we knew that the chemical composition was not going to reflect only chemical evolution, but was going to reflect also some stellar evolution issues. So these binaries that were already shown to be peculiar in the chemistry were removed. And this one here is not peculiar, but the fact that it's so much younger and very similar to here makes me believe that this star is a binary, and therefore the age must be wrong. So I think that that star is older.
Thank you.
Okay, we have a question from Stephen, if you would like to unmute yourself.
Hi, thank you, Paula, for an awesome talk. It's really fascinating to see some interdisciplinary work going on, borrowing from some of our sister sciences. But you mentioned quite early on in your talk the use of cosmological simulations. I was wondering if you've ever built one of these trees for, say, a star forming simulation, because that's one of the areas that I kind of work in.
Yeah. I mean,
some of these simulations have some level of almost like predicted physics when you build them, so you're inherently building in some bias. But I was just wondering, see, for more of a complete population, what would you find?
So I did some attempts kind of 2 years ago with some cosmological simulations, but then I had another problem. As I said, everything we try to do, there is always associated with a problem and with a challenge, and then it's difficult. And then the problem is that I had too many particles. So for making, I had a tree that was huge and I had no idea how to interpret. So I think that I need to develop some tools that I know that exist, but I haven't learned them yet, to kind of see first how to group these particles in the simulations to then build the tree and interpret it. So that step is what kept me kind of a bit on hold on that. And also, in the meantime, the simulations have improved because they didn't have so many abundance ratios at that time. So now they have more because they have ingested more of these nucleosynthesis processes. So yeah, actually, we just got a grant in Chile with a cosmological simulator, Patricia Tisera, to work partly on this kind of stuff. So she's building all the simulations, and I am supposed to make trees on the simulations.
Great, thank you.
And also now I got also from chemical evolution models, I got some models finally, actually yesterday, so of dwarf galaxies, which are simple, who haven't interacted. And then that is a very important thing that we need to investigate, because here, this is from data, and we can never really know, for example, if this clump here or that clump here are real, right? But from a simulation, of course, we can know that. And yeah, now I have a few simulations to start playing with it.
Great. I have a very quick question, which is, have you thought about applying these trees to the Gaia Encelada sausage system?
Yes, that is where we're trying to go ahead. That is the idea of Daniele's PhD thesis, in fact. So first we need to find a very good way of selecting Gaia Encelada stars. Then we need to find the best way of getting extremely accurate and precise abundances, because these are metal poor stars and these are very distant stars, so uncertainties are a bit larger than here, and that may make the tree a bit more stable. So we need to improve the uncertainties, the better, or the best we can. And yeah, then is the question, right? These Enceladus stars, how can we really know that the star is coming from Enceladus or the star is coming from the Milky Way? How can we which are the best chemical abundance ratios that may tell us the difference? So yeah, that's the kind of thing that we're working together, Keith. But then yes, the idea would be after, when we have our clean sample, which you're very much welcome to help us in cleaning a sample, to make a tree out of it.
Great. Rob has a question. You want to unmute yourself? Okay, let's go to Agnesh. If you have your question, would you like to unmute yourself, please?
Amazing presentation, first of all. I was just wondering about this, that do you think that dark matter has some kind of like fundamental role in in the related like fundamental role of how a galaxy will evolve in a particular future scenario, as to if you can have some insights on that?
Well, I mean, at the end, dark matter, it's very important for the cosmological simulations, right? So for galaxy, I mean, galaxy formation is all governed by dark matter, because you have all these little dark matter halos, and inside you have the galaxies, and these dark matter halos interact, right? So dark matter in the kind of merging history of Milky Way, of the Milky Way or Milky Way-like galaxies is fundamental. That said, so I think that, yeah, dark matter kind of will dictate a little bit the gravity, the mass of baryons you may have in each of these in each of these halos, which eventually will tell you how much gravity you have to when you start forming stars, how much of the material can be retained in these potential wells and how much will be ejected out of it. This is where kind of in a global sense you have dark matter playing a role. At the level of kind of one star with the other in one cloud, dark matter is not so important, but kind of in an overall context, it is extremely important.
Thank you.
Cosmological simulations again would probably help to see, okay,
Yeah.
if I change a little bit my distribution of dark matter, I will get a different merging history, and that will be reflected in.
I think it's basically, it's very unique for every other galaxy, so it's kind of.
Yes.
Yeah. Thank you.
Great, thank you. We have time for about 2 more quick questions.
May I try again?
Rob? Yes.
Is the unmute work now?
Yes, you are good.
Okay,
now.
sorry, I tried the space bar. This is more of a, it goes back to, I think, Daniel's question at the very beginning. There are 2 or maybe 3 different velocity scales. I mean, there's one associated to gas diffusion, there's one associated to the orbital velocities in the galaxy, and then the merger of galaxies. They seem to be vastly different velocity scales and affect, you know, the ability of the different scales to interact with each other. I'm just wondering if you could comment on that, because it's those 3 values seem to have some effect on how to interpret the similarity of very distant parts of this galaxy and when different galaxies interact. But those are actual values that we have. So I'm just wondering how you.
Yeah, so for the kind of chemical evolution models, or from a way of kind of modeling this and trying to make it as simple as possible, we say that the gas is not able to move very far away. Also, we need to think that those that are really driving chemical, you know, changing the chemical composition in space are the massive stars, and they are very short-lived. So they don't have much time to really move out and go and explode elsewhere. So they kind of do it locally. But as models become more sophisticated, they can kind of include more long-lived stars to kind of have more time to go out of the birthplace and then explode elsewhere and pollute somewhere else. That is kind of what would be at the level of chemical enrichment in a galaxy. But then, as you said, like there are these other velocities of how galaxies interact with each other that could be probably more at the kind of cosmological level of how much merging of galaxies you have in the kind of lifetime of the galaxy. That would be, and then the efficiency of how the 2 populations are kind of mixed. So this is slightly different. I think that stars eventually, they don't, a loma star that is having a chemical composition there, its spectrum, it doesn't really care very much whether there is a merging or not. It will change its orbit, but nothing more than that. But then the gas in these galaxies, it could be mixed. And how it is mixed, I think that it's still kind of a big unknown. I mean, these are all parameterized in models in a way.
Okay, thank you.
Great, we have time, unfortunately, only for about 1 more question. If Monica, if you want to unmute yourself.
Hi, so thanks. That was a great talk. I was just wondering whether you'd considered, since you have, this is Gaia, a lot of your stars are in Gaia, so there's 6 phase space coordinates from which you could calculate orbital actions, assuming you have some sense of the potential. And since orbital actions are conserved under, adiabatic sort of evolution of the galaxy, actually even not so adiabatic necessarily, you might find that even stars which are chemically or which you think of as being as twins from your analysis might actually be very close in action space, and even if they're not at all physically close by, and they may have very different velocities as well at the time you observe them, but in their actions might actually be quite close. And so have you considered looking at that?
So actually we did look at that. So here because I chose the birth radio as kind of the dynamical plot and the eccentricities here. Oops, how can I take this out? So, well, I don't know why now. Anyway, sorry, it's like technical details. I'm a bit overwhelmed with them. But yes, we did calculate the actions and the angles of all these stars with Gaia and the velocities, but trying to find, because we wanted in particular to study a little bit these clumps here, no? So to see if they were kind of more connected or they were kind of more connected. But I think that we still don't have enough stars to say so, particularly the old stars, then the birth radii become kind of uncertain. So we didn't have enough stars to be able to see like real clumps in phase space, to see how they lie in the tree. I think that for that we need more stars. So the only thing that we could kind of find was kind of, it makes sense to see that the old stars have kind of a variety in eccentricities, and they are kind of kinematically hot. Also kind of the actions also show that, and that they are coming from inner parts of the galaxy. So this is all can be kind of explained using astrophysical arguments, which is kind of encouraging, but kind of discovering here a clump in phase space that is related to a clump in the tree, that unfortunately we didn't. And initially we thought that maybe the burst was going to be kind of a cluster in phase space, but they are spread, which was interesting because that kind of tell us that if there was a star formation burst that was produced after this major merger event, that star formation burst must have been quite efficient, across extended region in the galaxy. And I think that this is very interesting.
Mm-hmm. Thank you.
Thank you. I think we have just one question left, one raised hand left. So I want to just get to that last person. Alison, if you want to ask a quick question.
I'm sorry if I've missed it, or I think that the question may already have been answered, but in the sort of phylogenetic diagram, the thing that looks a bit like somebody's ear, there's a sort of cluster amongst the very old stars. There's a sort of event of some sort of dynamical event, a merger or something. And I just wondered, since you have ages for these stars, presumably, if that ties into any known merger event that's happened.
So which cluster do you mean?
Well, if you get up the sort of curved line plot again, it looks like somebody's ear. Yeah, that one. See, towards the top there, there's a big cluster that that's the one. Yeah. Yes. Does that correspond to any known merger?
Yeah, this is what we claim. We think that this cluster here corresponds to kind of the effect of the star formation that may have been produced after the last major merger event that we know that happened about 8 to 9 gigayears ago.
But it's not known what? It's not...
Well, I mean, there is evidence that there was a merger, and that this merger was produced by a galaxy, which could be one or two, or a combination of galaxies. We still don't know. That is called Enceladus nowadays, or such, depending on which paper you want to refer to. But that's kind of event we know that happened kind of at 8 to 9 gigayears ago, and it has been possible to identify these stars in the halo. From there, it's possible to kind of know the mass of that system, which is about 10% the mass of the Milky Way. We also have evidence from that the stars that were part of that galaxy have a different chemical enrichment history, because they have differences in their chemical compositions with respect to the old stars that were formed in situ. So that is all known, but there are indications that such an event may have also triggered a star formation burst in the disk. This is kind of seen known mostly from models, but here we can kind of link it very nicely with this anomaly here.
Yeah, thanks. Very interesting. I'll look it up.
Awesome, thank you. Well, let's thank Paula again for a very nice talk. Do my little clap hands reaction here. And it's been a pleasure having you all. And I think just one last announcement that there's a public lecture on Thursday at 5:30 Aspen time. I think that's it for us.
Thank you for staying, and I apologize for the Zoom and my keynote being mad with me.